John.
Okay, can you see it?
Yes, perfectly.
Okay, fine. So, shall I start?
Yes. You are the master.
Okay. So, good morning, everyone. I'm Luis Garcia-Mozos, and I'm trying to summarize in 5 minutes the progress of my research project. So, the title of my research project is BFS. This is Back from Space, and it's supervised by Stefan Heinrich, CEO of e.NOVA Aerospace, which is the company that supports and helps me for this project. So the goal of the project, in few words, the final objective of the BFS project is to develop a re-entry kit that is capable to retrieve different devices from space in a safe and controlled way to retrieve the payload safe and sound to ground. And to this end, and putting more into words the project itself, e.NOVA defined these 12 Hercules works of the BFS project that include from the global system definition, trajectory calculations, and thermomechanical aspects to the study of possible customers that would fund the cost of the system. So therefore, these 12 works will be the skeleton of the project, and I particularly will focus on the most challenging case, which is to retrieve, which is to fit the whole system in a 3U spacecraft and trying to retrieve it from the ISS orbit. This will give us no other option than using a small deorbit burn and try to land only with a ballistic descent without any active control or guidance system. So this leads us to the main issues of the project. Of course, they are mainly related to the need of fitting everything in such a small device, and we need therefore the simplest possible design. The main difficulties are firstly the large number of our centrists that are on the system due to the early stage in which we are working on. And also there are a lot of complex technological and scientific domains that converge in this topic at the same time. So we'll have to deal with hypersonic aerodynamics, heat transfer issues, deployment of mechanisms, and all these with very recent technologies that have not been fully developed and mature yet. So let's move on now to the milestones of the project. The timeline proposed is based in addressing sequentially different groups out of the 12 Hercules works. After the literature review, I have already started working on the study of the trajectory and especially in the landing position accuracy. And in parallel, I will start soon working on the detailed definition of the system that will entail selecting an appropriate cold gas propulsion configuration and the general architecture of the braking and landing systems. After this, I plan to work on the aerothermal analysis and flexible thermal protection systems, and then I will spend 3 months until the end of 2021 studying the mechanical aspects of the system. And for the last leg of the project until March 2022, I will study the cost of the device and the different platforms and payloads that would stand as candidates to pay for our kit. So I'm going to talk briefly now about the state of the art of the project, and to illustrate this, let me show you this picture that represents the evolution of the different re-entry technologies from the Apollo missions or the space shuttle to the last Martian entry missions, and the technologies that are to come here, from which I want to highlight, for example, the HIID mission that studies inflatable decelerator devices. So I have therefore carried out the state of the art on the different technologies that are expected to be used within the project, like the before mentioned inflatable devices here, or deployable accelerators like this one from NASA, or flexible thermal protection systems, etc. And together with this, I have performed research on more technical documentation in terms of analytical re-entry analysis. And in this context, I will use, for example, some pedagogical documentation from the FAA or the SMAT handbook that is always useful. And all the bibliography is being gathered in both a PowerPoint file with one slide briefly describing every document and in an Excel sheet compiling the basic reference information. So finally, I would like to comment something about the first task that I have started to develop within the project, which is the study of the landing accuracy. We talk about an unguided descent from the ISS to the ground that will be only controlling the initial instant with the orbit burn impulse. And from this point, the spacecraft will follow a perturbed Keplerian motion to the ground. In this line, I have found from literature review that an important factor to improve the accuracy of the landing is to reduce the time in descent while we try to keep deceleration and heating rates under control, of course. And given all this, the main sources of error for the landing position are found to be errors in the value of the orbit burn and in the initial position and attitude determination, and the uncertainties in the aerodynamic and atmospheric models like ballistic coefficient determination. And thus, the objective is to land in some restricted military areas on ground that are also being studied. And the most promising one here is Woomera Range Complex in Australia, which I showed you a picture here. And this has maximal usable dimensions of almost 600 kilometers. And the idea is trying to assess whether it is feasible or not to land on these locations with the intended re-entry systems. Well, that would be all for my part. Thank you very much. And if you have any questions, I will be happy trying to answer to them. Thank you.
Thank you, Luis, and congratulations. You were perfectly on time.
Okay. It wasn't easy to fit everything in 5 minutes.
I know. Is there any question from the people in the audience for Luis? Or comments or? Okay.